Hello students, and welcome to your first lecture for online learning. We're going to start with fossil fuels, and part one is going to be pretty short, as we're just going to talk about energy laws and uses of energy globally. So we're going to start with power. Power is the rate at which work is done. This is like basic physics 1 stuff, and energy by comparison is the ability to do work. So the joule is both a unit of both work and energy. Power is defined as the rate that it's being done, so it's energy per time, otherwise known as work per time. So we have our units here, and if you look, generally these metric units you should already be familiar with, but a kilowatt is how your house's energy would be measured. You get a bill of kilowatt hours. How much energy are you using versus how many hours are you using it? Megawatts would be like the amount of capacity for a local power plant. As you start to get into nations' power supplies, you might be talking about gigawatts, which is billions of watts, and then terawatts if you're looking at the amount of energy being used or power being used for the entire planet. All right, and then over here you can see kind of some comparisons of different amounts of power that, that different light bulbs draw. All right, so energy, this again is physics 1. You have kinetic, which is energy of motion, and the potential, which is stored energy. And these two types of energy play into our various types of not only fossil fuels, but nuclear. Nuclear, say would be potential energy until you start causing that chain reaction, and then you convert it into kinetic energy. For water, hydropower, you would have potential energy stored behind the dam. And then as soon as you let that water drop, it could turn into kinetic energy at the base of the dam. And we'll be talking about how power stations work. But with a hydropower plant, it's that moving water that will spin the turbine. And whenever you're making electricity, you need to spin some sort of turbine. And that generates the current, which can then be piped off to your houses. All right, so there's a few laws, energy laws. And the first law you all already know from, again, physics, is basically energy is conserved. You can neither create nor destroy energy. We know this as the law of conservation of energy, but it's also called the first law of thermodynamics. The implication is that you can keep some sort of bookkeeping, that energy never actually goes away anywhere. So you might be wondering, well, why can't we just always use the same energy over and over again? And we'll get to that with the second law of thermodynamics. All right, so you can't get something for nothing. That energy has to come from somewhere. And you can break that law with Einstein's equation, but that's really not related to this class. So I put up this picture of the tidal stations, the tidal power, because you might think, the tides are moving. Why don't we just harness that power, get that energy out of that water, make electricity out of it, and pipe it off to our homes? We live in an area with a lot of tidal movement. One of the unintended consequences might be that if you're taking the energy out of the water here, it may not be reaching the shorelines where you have that intertidal zone that might be dependent on that energy. So you always have to kind of think, if I'm taking energy out one place, is that going to have an effect down the road? All right, so just a little joke for physics jokes. And moving along, the second law of thermodynamics is why we can't just keep reusing the same energy over and over again. And that is that once you use energy once, it goes from a more useful form to a less useful form. And that less useful form is actually usually heat. And heat is a very hard sort of energy to capture and use for things. You can, but it's just not as easy. So another way to look at it is that entropy, a measure of disorder, goes up as every time you use an energy source. And again, that degraded form of energy is usually in the form of heat. All right, so as we evaluate our energy resources, there's different sorts. These are graphs for your more developed nations versus your less developed nations. And notice that fossil fuels, which is using some kind of biomass for your fuel, is really prevalent in both types of nations. In your developed nations, you have oil, coal, and natural gas. Your biomass, which is like burning wood, peat, etc., is less common. In your developing nations, that's a much more common type of energy. And notice the slices of the pie currently for your renewables is not very large. But that is something that these numbers are already probably out of date. We are actually increasing our renewable slices of the pie yearly. It's one of the big changes I see as a teacher in this class. All right, so energy consumption per capita, yes, we are very large. There are a few countries larger than us. It looks like Iceland might top us, but they are a big volcano. They are sitting on all the geothermal energy they could possibly use. So as far as per capita consumption, yes, we are one of the greatest in the world, along with Australia, Canada, and a few other countries. All right, so when you're looking at renewables, and we'll be getting more into this with our unit, 2 units down the road after we do nuclear, there are all sorts of renewables. And again, this slice of this pie is increasing. But for right now, we are still highly dependent on oil, coal, and natural gas for our use. And as far as total world energy consumption by source, notice this is as of 2013. Notice what a big amount coal still is. So, and again, we'll be talking about each of these in turn in our following lectures. All right, so world energy consumption over time. Do notice that, so again, biofuels go down as people stop burning wood for fuel and use the other types of fossil fuels. And again, look at nuclear energy kind of took off in the post-World War II era. And also note that coal really took off kind of in the late 1800s, early 1900s. And this down here is actually starting to really decline. When we look at our coal lecture, we'll see that coal really is decreasing worldwide. All right, in the US, what does it look like? Who's using the energy? So look at the big slice of pie that industrial sources are. So plants, all kinds of factories, et cetera, are a huge use of energy. Transportation comes next, and when you think about conserving energy, people talk about using, electric cars, different sorts of cars, but transportation is a big piece of the pie, not quite as large as industry. There's commercial, like office buildings, et cetera, and then residential. You are all at home right now and you're heating your houses, most of you probably with natural gas. Second most common would be electricity. And then if you were like me and you live in an old 1950s house, I actually still heat my house with oil. So this is just a showing over time what those different amounts look like and how it has increased in the US from say 1950 all the way to 2015. All right, and then in the US, again, this slice of the pie is getting bigger, but as far as our uses, notice that coal is actually a much smaller piece of the pie now, and that is starting to go down. So we still use quite a lot of oil, otherwise known as petroleum, and natural gas. We have actually been increasing. That's one of the reasons why our coal use has been decreasing, is that natural gas has been going up. So as far as what we're producing by major source, again, natural gas, mostly due to fracking, has really increased over time. All right, so then again, just comparing us to other areas of the planet, our renewable piece is still a smaller piece of the pie compared to some other countries. But again, this breakdown isn't too different between the world and what the US is doing. All right, and then by country and region, just looking at who are the big players. China, because they're so large. Us, we're the 3rd largest country. India, even though they're going to be population-wise the largest country in the next decade or so, they are not as big energy consumers, at least not at this time. But if you look at energy per capita, this graph down here is interesting. The United States is the gray. It actually looks like the Canadians might use more energy per capita, and it might be that because they're in a much more cold climate in the wintertime. I'm not sure all the reasons for that, but we used to be #1 for energy consumption in the world, and that has actually shifted and shifted fairly quickly. So again, this happened since I've been teaching this class. I used to always say, yes, we're #1 for energy consumption. Not that it's a prize we want, but in the last decade that has changed. So now China's the biggest consumer. All right, I just like this one. You don't have this one in your notes, but if you wanted to say like how much energy do we use, like us here in Washington, we use as much as like the country of Algeria. And just it's kind of amazing when you think that we're so large and we use so much energy that say Texas uses the same amount of energy as Brazil. This just kind of blows me away. All right, so this is from your book, so I don't want to dwell on it, but realize that while our total energy consumption has been going up in this country, that's a lot dependent on the fact that our population has also been increasing. If you look at our energy usage per person, it's actually remained fairly stable from the 1980s till the current time. And that is surprising, because if you think we use a lot more electronics than we used to, we're driving bigger and heavier cars than we used to. But a lot of this has to do with energy efficiency, and that we're using our energy more efficiently than we did, say, back in the 70s and before. All right, so there's something called net energy. And that's the total useful energy available from a resource over its lifetime minus the amount of energy used, automatically wasted and unnecessarily wasted to find, process, and transport it. So the idea of net energy is kind of like net primary productivity. It's how much can you make extra over what you're consuming. So if you're wasting 8 units of energy for every 10 units you get out, you only have a net energy of 2 units. So this is where efficiency can come in. Energy sources with a high net energy are going to be better. We can get more out of them compared to what we waste. All right, so the ratio is the ratio of useful energy to what you're using to produce it. So in that previous example, if we get 10 units out, but we spend 8 units just trying to get it out, or in the extraction process, we only have a net energy ratio of 1.25. So when we look at our net energy ratios, why is it that fossil fuels are so common and why do we use them? They have really high net energy ratios. One of the biggest advantages of fossil fuels is that you get a lot of bang for your buck. And I mean that for the amount of energy it takes to extract those resources, we get a lot of energy out of it. A lot of our renewables don't compare as favorably to that. So as we start to look at some of our other sorts of things, they're not as high. So as we look to start replacing our fossil fuels, we're going to have to worry about this net energy situation. And can we improve, say, our solar panels, et cetera, so that their net energy ratios go up? This is again from your textbook, so you can always go back and look at that too. All right, so I believe this is the final slide for part 1. And as we look to evaluate not just coal, oil, and natural gas, but as we look to evaluate nuclear, hydro, wind, all of those renewables, what do we need to be looking at? All right, so first off, how much is available? Like, you know, solar in this area may not be as great. Solar in Arizona, awesome. Coal, we've got tons of coal in the United States. Other countries may not have many coal reserves, all right? So how much of it's available and how much of it can we produce locally, you know, versus having to import it, say? What's the net energy yield? So how much, you know, energy do we waste just trying to get that source versus how much can we actually use? How much does it cost to develop, phase in, and use? And this is another huge advantage currently with fossil fuels is that the infrastructure is there. So we've already got the infrastructure for a fossil fuel economy. Replacing that infrastructure with renewable infrastructure is going to cost. Once we have it, however, that would change. All right, and then how does it affect the environment? This is a big disadvantage of fossil fuels in that it has a high environmental cost. And then finally, what will it do? What will using this energy source do to help sustain humans and other species living on Earth? And this is related to the environmental cost, but you know, how helpful versus harmful is it? So that is the end of the first lecture, and I will go ahead and stop the recording if I can figure out how to do that, and we'll see you guys for part 2.